Okay, great. Hi, everyone. Good morning, good afternoon, if you are on the East Coast. I'm Liang Fu from MIT, and it's my great pleasure to welcome and introduce our CIQM seminar speaker, Jen Cano. Jen is from Stony Brook. She's actually visiting MIT in person, and what you see is she's standing next to me in our two-box seminar room, and this is really the first hybrid seminar in the CIQM series, starting from the beginning of the pandemic. So yeah, a few words about Jen. Jen got her PhD from UC Santa Barbara in 2015, and then moved to the East Coast. So she became a PCTS fellow at Princeton University. This is the Princeton Center of Theoretical Sciences. And then in 2018, she joined the faculty of Stony Brook. And Jen has done many interesting and important works in quantum Hall systems, in topological materials, and more recently in moiré systems. She's one of the main contributors to the topological quantum chemistry that lead to the identification of numerous thousands of topological materials. And today, she will tell us about her very recent work on combining topology and moiré systems. And so, floor is yours. Yeah, Jen, please.
Great, thanks a lot, Liang. Okay, give me a second to share my screen. Okay, well, let's get rid of this. Okay, great. So thanks for having me here. Thanks for the in-person audience also. People on Zoom who have a question can type their question into the chat, and Naomi will try to relay those in real time if possible. So today I'm going to talk about two different topics. We'll see what we have time for. So first, I'm going to try to convince you that in addition to the first magic angle in twisted bilayer graphene, that it would be interesting to look at the smaller magic angles. I think that there's different physics there, and I'll explain why that is, and then also discuss some caveats. And then in the second half of the talk, we'll switch gears and discuss some extension of the twisted materials, which is what happens if we apply a superlattice potential to the surface of a topological insulator, and then see if we can transfer the physics that we see in twisted bilayer graphene to 2D Dirac cones, to the Dirac cones that are on the surface of 3D topological materials. So those are the two things that I'm going to try to talk about. And let's see. Of course, it always works when you practice it. Now, does the clicker work? Yeah, okay. So great. So of course, we know why we want to study twisted bilayer graphene, because it gives us this tunable platform to realize correlated physics. And to this audience, I don't really need to explain it. We experimentalists have seen correlated insulating phases, superconductivity, and quantum anomalous Hall effect all in graphene, which is pretty miraculous. And this is all due to the correlated physics that appears when you get these extremely flat bands. So we don't know the exact mechanism of these correlated phases, but we know that they're due to flat bands. And in this talk, I'm not going to be focused on twisted bilayer graphene, but what I want to say is that we're trying to achieve flat bands in different systems and see if we can carry over that same technology. So, so the starting point for this that we're going to keep coming back to is generalizations of the Bistritzer-McDonald model. So I just want to give a little introduction to that model. So the idea is that all the low energy physics in graphene is at the Dirac cones. And so we only need to consider one Dirac cone from each layer, which gives us a picture like this. And we only need to look at one valley because the two valleys are far apart from each other. So we're just going to stay in one valley. We have one Dirac cone from each layer. Their energy spacing, or their spacing separation is determined by twist angle, and they cross. And it's the interlayer coupling that opens up this gap. And so there's some balancing point between the energy scale from interlayer coupling and the momentum scale from twisting, that when those things balance each other out, then we can get these kind of really flat bands coming from the Dirac cones in graphene. And it's not clear why those bands would have to be flat, but what is clear is that we can get the velocity of the Dirac cone to 0. And so the Bistritzer-McDonald model predicts this velocity to leading order in perturbation theory, and they predict that with surprisingly good accuracy. So that's our motivation for carrying out perturbation theory in other systems and hoping that at low orders in perturbation theory, maybe we can still capture the physics of the system. As I said, in that argument, we don't know that we would get completely flat bands, but band structure calculations confirm that. And so this is a calculation of the Bistritzer-McDonald model. We can see these kind of flat mini bands forming, and we can see that the density of states from freestanding graphene gets severely enhanced by these flat bands. So that's the thing that we're going to be looking for always as a key to correlated physics, enhancements in density of states near the Fermi level. And this right-hand picture is showing ab initio calculation when you actually do your first principles calculation and allow atoms to relax, then this flat band becomes nice and isolated from the conduction and valence bands. And one of the points that I'm going to come back to is that all of the physics that's been observed so far is at the first magic angle, but it was predicted by Bistritzer and McDonald that series of magic angles where the velocity vanishes. And so that's one of the things, like I said, I'll come back to. This is around, this largest angle is around 1.1 degrees, then it's around half a degree. This is the prediction from their model at least. So the angles get quite small. Okay, so the model that we actually want to study is an even further simplified model, which is this chiral model of twisted bilayer graphene. And in this model, the nearly flat bands in the ab initio calculation become exactly flat bands, and they're analytically solvable. And so that's one of the reasons why this model is actually quite fun to look at. You get perfectly flat bands, and you know exactly what the wave functions are. And so just to give a little bit of insight as to how this happens, so this is a schematic setup for the Hamiltonian for twisted bilayer graphene. So this is the top layer of graphene Dirac cone, bottom layer of graphene Dirac cone, and we have this interlayer coupling. And the interlayer coupling is a 2x2 matrix. And because the A, B, B layers are the same as each other, it can't have, this 2x2 matrix can't have a sigma z term, but it can have an identity matrix term. So that gives us one free parameter. And it can have some off diagonal terms, and that gives us a second free parameter. And because of the rotation symmetry of the crystal, those are the only free parameters that we have for this model. They set these terms equal to each other. But in the chiral model, you can't see because the bottom of my screen is cut off, but they set the omega naught term equal to 0. And so what that does is say there's no interlayer AA or BB coupling, but there's AB and BA coupling. And also, if you have a question, I just saw one hand raised, you can type your question and it will get read. And so if you do a basis change model, it nicely diagonal off becomes block off diagonal, A sublattice and B sublattice. So this shows you there's no AA and BB interlayer coupling, but we have this off diagonal coupling. And this is actually what gives the name chiral model, because these blocks are completely off diagonal. So the Hamiltonian will anti-commute with a poly sigma z matrix in this basis. So it has a particle hole symmetry. So that's where the chirality comes in. But the other nice thing that happens is that you can see that zero energy solutions to this are going to be two component spinners. They'll either be 0, 0 something or something 0, 0. They're going to be zero energy eigenstates of either this 2x2 matrix or that 2x2 matrix. So the flat bands, which are the zero energy states, are only two component, and they're either localized on the A sublattice or the B sublattice. So in this simplified model, the flat bands have sublattice as a good quantum number. We can understand some of the topological properties that I've seen, or at least this gives us some hint as to topological properties. Because if we just look in one valley, we get these two flat bands. One is localized on one sublattice, one is localized on the other sublattice. And because we can exactly solve for these, we can see that they have a Chern number. So the bands on one sublattice will have one Chern number, other sublattice will have the other Chern number. And in the opposite valley, the Chern numbers will be reversed and they'll be related by time reversal. So if you take your twisted bilayer graphene and put it on a hexagonal boron nitride substrate, that breaks the AB sublattice symmetry. So that will pull two of these bands down in energy. And then in order to see quantum anomalous Hall effect, what you need is spontaneous time reversal structure breaking. That's the only remaining ingredient, which we can't get out of this band structure model. But this gives us some insight as to where the topology comes from. Once you spontaneously break the valley symmetry, then you'll have one of these bands with Chern number 1 or more than the other, and that's how you'll be able to see anomalous Hall effect. Question? Yeah. Questions? I mean, maybe we can look at the chat here. Okay. Please type questions into the chat window. Okay, so far there's no actual questions. I don't think I can address the hands raised because they can't speak if we, yeah. Naomi, do you want to ask people if they have questions? Okay,
I mean, I wrote for them to type them into the chat, so I'm hoping that people do that.
Oh, right. People should type their questions in.
Yeah, so they can all see that. Everyone can see that.
Great, thanks. Good. So
hi, this is Bob. I think if they ask the questions where you are, and if you just repeat the question and you're on the mic, I think we're good.
Okay, but they have to type the question into the chat.
No, if you're looking at somebody in person there, just ask them to ask the question.
Oh, in person, yes.
If you just repeat what the question is, then we've all got it.
Oh, got it. Right. If there's questions in person, just ask it and I'll repeat it. Okay. Please do ask questions if you have questions. Okay. Good. So, right. So now getting into our own work. So we're studying this chiral model. And so first we looked at analytical properties of this model. And so I just want to highlight, unfortunately his face is blocked, but this is work done led by Ji Wang, who's a postdoc at Flatiron Institute, who's been leading work. Good. So, right. So the first thing that we did was realize that there's actually an extra inversion symmetry within each valley. And that gives us extra information about these wave functions. And so then what we can see is that these flat band wave functions, so remember there's 4 flat bands, 2 in each valley and 1 on each sublattice. So once we know one of them, we know all the others because they're all related by symmetry. So these wave functions have to be eigenstates of this operator. It anti-commutes with these D matrices, but those are off diagonal. So this actually commutes with the full Hamiltonian. So all the eigenstates are going to be eigenstates of this. And so that tells us that the wave functions, that gives us some information about the wave functions. And then the rest of the information we can deduce, well, we can just deduce from the rest of the Hamiltonian. So basically we just need to now find one component of the wave function, and then we can find the other component, and then we can find the other flat bands. So we found that the flat bands factorize in this way, and I want to explain each of these terms. So the first term is a quantum Hall wave function in the lowest Landau level. So this is something that we're familiar with, and this is where the topological properties or the Chern number of this flat is coming from. The second term is an quantum Hall wave function. So in other words, it would see the opposite magnetic field, but it has a fixed K index of the capital K point. So this doesn't affect topological properties, but it ensures that we're getting block wave functions. So basically quantum Hall wave functions satisfy magnetic translation symmetries. They don't satisfy the block symmetry properties. And so by combining quantum Hall and anti-quantum Hall wave function, that's the only way that we can get a block wave function. So that's kind of a general statement of Chern insulators. And then finally, there's this third term. This is the thing that distinguishes all of the different magic angles. Different solutions for this row will correspond to different magic angles. And this function rho, so this is a cell periodic function because now we have all the right periodicity from this quantum Hall and anti-quantum Hall wave function. And so this thing has to be cell periodic. And the different solutions will correspond to different magic angles. Yeah, I'm gonna see if I can move this thing. Yeah.
The Hall part of the wave function is labeled by small k.
Yes.
Which is the block momentum.
Yes.
While the anti-quantum
yes.
part is labeled by capital.
Yeah.
So can you elaborate with
Yeah. So the question is why do the two quantum Hall wave functions have little k and capital K index? So basically, if they were both little k, then there wouldn't be any Chern band. So what I want to say is this function has a churn number, and it doesn't, but it doesn't have the right periodicity. This function combined, since they have they see a net zero field, combined, they give you a block wave function. But because this doesn't have any dependence on K, it's a fixed K point, it doesn't change the topological properties. So it's this combination that gives us a churn band. That's a block wave function. Yeah, got it, thanks, good question. Right, so this function rho is kind of the only ingredient that changes from magic angle to magic angle. The rest have these quantum Hall and topology parts which are baked into it. And so now if we want to study things that change between the different magic angles, then we just can study this function rho. Okay. So, so the thing that, right, so what I said in the beginning is I want to, we're going to try to look at some properties now of these flat band wave functions and compare properties at first magic angle to other magic angles. So the first thing we want to look at is charge density. So what I'm plotting here is I'm picking one K point. Actually, it's just the capital K point. I'm looking at the wave function and I'm plotting it in real space. Okay, so this is charge density in real space for one of the flat band states. And what you see, so it has, remember, it's a component spinner, and which means it's localized on one sublattice, but it has weight on the top layers of the bilayer graphene. And so what we see is that there's some peak in the center and there's some vanishing points at the corners. And these vanishing points are actually exact nodes. We can see this because if we look at those, we can see this analytically. If we look at the wave function I showed on the previous slide, we'll see that the quantum Hall and anti-quantum Hall wave functions have 0 points, and it's those zeros located at these corners. So that's what the charge density looks like. And this is kind of a reality check for what we see in the experiment. So in twisted bilayer graphene, if you look at charge density with STM, you see these peaks, and there's one peak per Moire unit cell, and that's the same feature that we're seeing here, one peak per Moire unit cell. So that's at least some small reality check for this model that we're studying. So what we next want to do then is look at the charge density at the other magic angles. So this top is the same thing, the same plot that I showed on the previous slide. This is the first magic angle. But what we see at the second and third magic angles is that we see that the peak structure is very different. And what we can understand is actually, the thing we can understand analytically is that these purples, so purple is small on the energy scale, red is large, these things are exact zero modes. And as you go from first to second to third magic angle, you see that these nodes increase in number, and they always need to increase by 3 because we're looking at the K point, it has a 3-fold rotation symmetry. And so because these nodes are accumulating at the center of the unit cell, the charge density gets pushed out. So we have some prediction here, which is that if you could access these second and third magic angles, and if you looked at them with STM, you would see a different pattern in charge density, which is multiple peaks within the Moire unit cell, which is never observed before. So far, all the cases that we've seen have one peak in the Moire unit cell. So that's kind of interesting. Beyond that, there's also an interesting consequence, which is if the charge density is different, that means that the projected Coulomb interaction is almost certainly also different. And so that gives us some reason, so we haven't done this yet, but that gives us some reason to at least explore these other magic angles, at the very least explore them theoretically. What is the projected Coulomb interaction, and what are the different types of correlated phases that would occur when the Coulomb interaction is different? So that's one reason why I think these second and third magic angles or beyond they definitely will exhibit different physics, whether it turns out to be the same in the end of the day or the same interacting phases are stabilized. That's a problem that needs to be worked out. So the other thing that I wanted to say is that I mentioned these nodes, which are places where the wave function vanishes exactly. And so we can actually understand these in a little bit more detail. So I was previously showing the wave function charge density at the capital K point, but we can look at that. We can look at wave functions at every K point and plot them all in real space. So this is an example of the charge density for a wave function at a generic K point. So it's a lot less symmetric because the generic K point doesn't have the same symmetry as at the capital K point. And so what we see though is actually that like most of these nodes stay exactly the same. So this is at the second magic angle. So we see these three in the middle, and then we see also the nodes at the corners. And the new feature that happens is this kind of node that's appearing in a very low symmetric place. And so what we learned from poking through the previous literature is that so as you change your K point, this node traces out the entire real space unit cell. And this is actually, a generic feature of a churn band. Anytime you already knew this, at any time you have a churn band, there's going to be 1 0 in K space that will move, and it traces out the entire unit cell, and all the other zeros are fixed. So this 0 is coming from the quantum Hall part of our wave function, which changes on K, and all of these other parts, some of them are coming from the prefactor rho, and then one of them is coming from the anti-quantum Hall wave function, and those ones are all sitting. So we can understand those zeros in that way. And we can also classify all the zeros. So here the zeros are these kind of dark purple points, but now we've just represented them by dots. And since our wave function is a 2-component spinner, each 0 has a winding number. And it turns out those winding numbers are either plus or minus 1. In principle, they could be any integer. And so these pluses and minuses are telling us about the winding of these zeros. And what we see then is that these zeros of the same winding, and they have to be the same because they are actually related by symmetry to each other. They get clustered near the middle. And so as a consequence, there's kind of a winding number of the net wave function, which is getting stronger as we get more of these zeros. So at the first magic angle, there's no zeros in the middle. At the second, there's 3. At the third, there's 6. And so this kind of winding gets enhanced. And so this made us think, well, we should also be looking at the orbital magnetization, because the orbital magnetization is exactly coming from winding of wave functions. And so that's the next thing that we looked at, which is we define this current operator, and we look at, it's actually a interlayer, intra-sublattice current operator. And we look at how this thing winds around. So I'm comparing here the first and second magic angle, and these little arrows are showing us the magnitude and direction of this current operator. And we're looking at the wave function at gamma, at K prime point, and at K point. And so we can see that the winding, you can see a net winding at the first magic angle. But at the second magic angle, you can see that this winding is getting larger. And we didn't plot it for the third magic angle, but we can speculate, since there's more nodes and they all have the same chirality, that it would continue to get larger. And so now this makes us believe that at the second and third magic angles, there's going to be enhanced orbital magnetization, which might mean that something like quantum anomalous Hall effect would be enhanced at these other magic angles. So charge density and the winding of the wave function are the things that become changed as you go from first to the smaller magic angles. And so those are the things that we think would be interesting to look at. Okay.
We have a question. Can this information be overlaid on quantum spheres showing the orbits of the qubits?
So I guess what we could do is, right, so what we're plotting here is a vector, and we're plotting it in the plane. So we could plot, I guess we want to plot magnitude and angle. So this is something which is kind of best plotted. I think it's probably best plotted in 2D. If we had fixed magnitude and 2 possible angles, that would probably be something like a qubit moving around in space, or moving around in phase space. So I'm not sure if there's a better way to plot this or to overlay it on qubits, but yeah, but I'm definitely open to suggestions. Okay, good. So so this is kind of the summary that I wanted to make of this first part. So what I wanted to convince you of is that these smaller magic angles will host different physics than at the first magic angle. They have a different charge density, which is a consequence that would be very easy to observe with existing technology. They have probably an enhanced orbital magnetization, remains to see exactly how you would detect this. And then I want to say something very optimistic, which is I think that why would I think that there might be more interesting phases with this? I said the Coulomb interaction will change as you go from first to second or third magic angle. Why do I think it might change for the better? Well, the interesting thing is that we can make a comparison to Landau levels. So if we compare the first to the second to the third Landau level, these also have an increasing number of nodes in the wave function. And you see different physics in the second Landau level than the first. And in particular, for example, you see the nu equals 5/2 state at the second Landau level, and you don't see it in the first. So, I mean, I'm really reaching here, but it seems possible then that if we have these smaller magic angles, which also have more nodes than at the first magic angle, that you might be able to see different and interesting phases that you don't see at the first magic angle. It's, you know, I think it all depends on microscopic details, but that's some optimism for why this would actually be interesting to think about more. What's the pessimism? The reason that the first magic angle is studied in experiment is because it's accessible. And the second magic angle is so small that what happens is that the twisted bilayer graphene breaks up into domains. So our whole model, it can be extended, but it's based on rigid bilayers. It's based on taking Dirac cones and coupling them. And if you're at the second magic angle, if your bilayers distort and relax, then you really need a whole new model. And so we need some platform where the second magic angle might be stabilized. And one place that I think is promising is possibly if we look at twisted trilayer graphene, because in trilayer graphene, the first magic angle is bigger. Instead of being at 1 degree, it's larger than that. So all the subsequent magic angles should also be bigger. So maybe the second magic angle in twisted trilayer graphene would be actually accessible in experiment. But okay, so that's something to look at. Of course, the other things that we want to look at, which are slightly blocked on the screen for in-person viewers, is this is all for the chiral model, but the chiral model is not real graphene, right? It makes this simplification that there's no interlayer A-B hopping. And so the thing that we're actually studying now is, do we see these same changes in the density of state as we go away from the chiral model? And actually, we have a lot of preliminary results on this. And what we see is that the nodes don't remain exact zeros anymore, but you still see changes in patterns. There will still be a different charge density at second magic angle than at first magic angle. That's something we can say for certain. We vary the ratio of these two AA and AB coupling terms, and we always see that pattern. So I think there's definitely something different at second magic angle. Right, and of course, the other thing we want to do in the future is study the correlated phases. That's the hardest and most interesting part of the problem. So that's something that we're thinking about and are starting to work on a little bit. Okay, so that's kind of the first part of what I wanted to say. Are there any? Yeah.
You made an analogy with the higher number level.
Yeah.
Higher number levels, I can understand the wavefront has to be different.
Yes.
It has to be orthogonal to the lowest one.
Yeah.
Here, we're really talking about very different angles. Like
right, the Hamiltonian is changing. Yes.
So there's some intuition behind it.
Yeah, that's a good question. Right, so the question is, you're actually changing the Hamiltonian at higher magic angles and you're not changing the Hamiltonian at Landau levels. So what's the intuition between these things? Yeah, so yeah, that is a good question. So I guess I've always thought of this function, what we observe is that function rho has increasing number of nodes as you look at the other magic angles. I wonder if we can think of it in this way. You can change twist angle continuously, but you only get flat bands discretely. So you might be able to think of this as if you're searching for zero energy solutions to a fixed Hamiltonian, you get them at different values of twist angle. Maybe, does that make sense?
Thank you.
Okay, maybe I'm convinced. Yeah. Yeah, but the thing that I can definitely say is this function rho has increasing number of nodes, and to me that seems kind of intuitive because anytime we study a Hamiltonian with quantized solutions, we always get more nodes as we go along. So I think that's kind of the picture. Yeah. Any other questions? Yeah.
So you said that at generic, you get like this
Yeah. Oh, right. So the question is basically, why do we see this extra node at a generic K point? Right. So what's happening is it's not actually extra. Actually, it was overlap. There was previously at the high symmetry K points, the nodes would be of order 2. So that thing at the K point, maybe I can actually just go back and show this. So for example, these top and bottom components, they actually all have 6 nodes. It's 6, but some of them are counted twice. But this is a double node. So here and here, it's actually the same number of nodes. And so then if we go to a generic K point, what's happening is that this double is moving off of the high symmetry point. And similarly here, one of these is fixed and the other one is moving off. So they all have the same number. There's just one that moves. Yeah. Good. Any other questions? Okay. And maybe I'll just look at this chat question. So the question in the chat is, what if the charge density has some irregularities in its occurrence at certain angle? Right. So I think we're only looking at the magic angles because those are the places where you can get flat bands. And so you could actually, one of the things we started doing numerically is looking in between the different magic angles, staying in chiral model, but looking in between to see how does this charge density evolve as you go from first to second magic angle. And it evolves smoothly. I'm not sure, I don't think I can say anything more specific about this, but there are irregularities in charge density, but they always have to satisfy these symmetry patterns. And we can kind of track how charge density changes as we change angle or as we change the parameters, the ratio of these interlayer hopping terms. And, and at this point, we're talking about just a numerical project because analytically, it's only tractable at the chiral model at the magic angles. Any other questions? Okay, so hopefully then I've given you some maybe some convincing that the first magic angle is not the only interesting thing. We can look at these second magic angles, and I think that kind of opens up a new direction to study in this field. For the second part of this talk, I want to move to something different, which is how can we extend this? How can we extend the physics of twisted bilayer graphene to other platforms? And of course, there's many different directions to go with this question. People are already doing this both in experiment and theory. But the idea that we had was Dirac cone. The other place where we can find an interesting Dirac cone is on the surface of a topological insulator. And so at a theoretical level, that Dirac cone looks identical to the Dirac cone in graphene, but the indices mean something completely different. Instead of sublattice, we have spin. And furthermore, this Dirac cone is at the center of the Brillouin zone instead of the corner. So there's similarities and differences, but from a theoretical point of view, then we can ask, can we tune the Dirac cone on the surface of a TI in the same way that we can tune the Dirac cones in graphene to get flat bands and maybe realize correlated physics there? So before I go on, I just want to mention my great collaborators, Xiang, who's now at MIT. Hopefully you guys will have a chance to work with him, and Justin and Jed. Justin just moved to LSU and Jed at Rutgers. So the first question is, why would we want to do this? So we're going to consider a Moire superlattice on the surface of a topological insulator. And as I just said, a topological insulator has a Dirac cone similar to graphene. But why would we want this? Well, the answer is that in twisted bilayer graphene, by manipulating the Dirac cone, we realize all these different correlated phases. And so here, the hope is, if the same thing could happen, it's not the same system, but if it could happen, we could realize correlated topological phases. That's what the point is. So that's our goal. Do we think that this actually would happen? The reason why I have some optimism is that in the early days when people were looking at TIs, they studied using mean field theory, mostly interacting instabilities of the Dirac cone on the surface. And the result from mean field theory is that an enhanced density of states will promote interacting phases. So in other words, the Dirac cone has some velocity, but the smaller that velocity is, or which enhances the density of states, the greater your instability to either Usually these phases are looking at a topological superconductor or a quantum anomalous Hall. And so so for example, the critical temperature for either of those phases will depend directly on the velocity of the Dirac cone. And if the velocity of the Dirac cone is smaller, then your critical temperature gets higher. So that's why we have some optimism that if we could manipulate the velocity of this Dirac cone, then we'd be more likely to realize these interacting instabilities. That's what we're thinking of. There's a major difference from twisted bilayer graphene, which is that you can't get a gapped mini band. So I showed earlier on that in twisted bilayer graphene, the flat band is isolated from the conduction and valence bands. Here, you can never get that because we're not going to actually study any interacting instabilities. We're just going to look at the band structure. And as long as you don't break any symmetry, then this Dirac cone has to connect the conduction and valence bands. So you can never get a flat band, which is gapped. You always need to have some Dirac cone in the middle of it. But nonetheless, as we'll see, you can manipulate the Dirac cone. Okay, so that's the thing that we're going to do. And we're not going to, what it says here at the bottom of this slide is that we're not going to actually look at the interacting stabilities. We're going to look at the band structure, and we want to see how can we change the band structure. That's what our goal is. Okay, so we want to put a superlattice potential on the surface of a 3D TI. How is this similar to Moire physics? In twisted bilayer graphene, what you're doing is making an enlarged unit cell and folding the band structure a bunch of times. And you get that enlarged unit cell because the two layers have two different periodicities. So now what we're doing here is imposing a different periodicity, but externally we're imposing it from some other potential. And we can see two routes to doing this. So the first route is, I'm showing on this side. This is bismuth selenide. We take some dielectric material, we punch a lot of holes into it, and then we put a gate underneath. And this creates some spatially modulated potential that will be felt on the surface of the TI. So that's one route. The second route that we're thinking of is, what if I put some 2D material on top of my 3D TI surface? And if these two layers are lattice match or nearly lattice match, and then I twist them, then I also will get some kind of modulated superlattice potential. So, and what we were thinking of specifically in this case is, let's take this 2D layer to be an insulator. And the reason that we want to do this is because if this 2D layer on top is insulating, then it's probably not going to have any interlayer hopping. Its only effect is to create a potential on the 3D TI. So these are our two different routes, which will ultimately lead to the same Hamiltonian, which will be a surface Dirac cone and some potential on that Dirac cone. So that's the thing that we're going to study. And just to take this question from the chat, won't the graphene structure affect if we change its lattice surface for the convenience of our observation? Right, so whatever material, yeah, and these heterostructures are it depends a lot on the material details. And so it may be that whatever material we choose to put on top of the 3D TI, it could get distorted, it could get buckled. You know, these are all instabilities that a person would need to do an ab initio calculation, and relax the atoms to see what happens. But we're not really worried about that at this level. All we want to do is consider there's some periodic potential on the surface. Okay, so then what I want to show is how we study this Hamiltonian. So the Hamiltonian is 3D TI Dirac cone and a periodic potential. And there's three things that I want to say about this. First, we'll do perturbation theory. So this is where the Bishitzer-McDonald model comes back. And like I said before, we're motivated by the fact that the Bishitzer-McDonald model works so well in twisted bilayer graphene. So we apply the same kind of idea here. And then we study two toy models. And these toy models are actually 3D models where we impose the potential on the surface. So I'll explain what they are when we get there. Okay, so starting with our perturbation theory. So again, this is our Hamiltonian. It's just a continuum model of a Dirac cone on the surface of the 3D TI, and then some superlattice potential. And this potential is defined by some wave vector Q, or maybe multiple wave vectors, which are related by symmetry. And so the first thing that we do is we compute the velocity perturbatively. And now it's imperative that I can move this little screen so you can see the main result. So we do this perturbative calculation. What we basically do is compute the self energy to leading order in this potential. And this is the renormalized velocity that we find. V star equals V over 1 plus alpha. And alpha is given by this. So it has a numerator and a denominator. In the numerator is the strength of the potential. So as you turn up the strength of your potential, alpha gets bigger, which means that our velocity gets smaller. Okay. And the numerator is based on this wave vector Q. So this moves in the opposite direction as you make your unit cell bigger. So in graphene, that would be like small twist angle. Then Q is getting smaller. And when Q gets smaller, alpha gets bigger and velocity gets smaller. And so those are the two different ways that we can at least perturbatively see that we change the velocity of the Dirac cone. We can change the potential strength, or we can change the wave vector, which is like changing twist angle. And in that language, smaller twist angles give us a smaller velocity. And so now we can already see one of the major differences between this system and the twisted bilayer graphene system, which is there's no magic angles here. This thing is never equal to 0. We can increase alpha, and in this model, we can increase it without bound, so it may approach 0, but it's never going to hit 0. And I think that intuitively aligns with the idea that we can't get these completely flat mini bands. Okay, so that's our that's how the perturbation theory works out. And then the other thing that we can do perturbatively is we can actually let me just say it like this. So this is our original Dirac cone, and we have our superlattice potential. And what the superlattice potential does is it has some wave vector Q, and it couples opposite points of the Dirac cone that are separated by that wave vector. And when these points couple to each other, they create satellite cones. So if this is our original Dirac cone, the band structure folds a bunch of times, and it creates these satellite cones at the corners of the moiré Brillouin zone. And these satellite cones, unlike twisted bilayer graphene, they can't gap because of time reversal. And so twisted bilayer graphene, the corners of the Brillouin zone are the K points. They're not time reversal symmetric. Time reversal mixes the two valleys. So this is a little bit different. We can't gap these. And so one of the main results, if you apply this superlattice potential to the TI surface, is that you'd get this series of satellite cones. Each one of these is its own little cone. It has its own velocity. And we can track these things using perturbation theory, and numerically, we can track their energy and we can track their velocity. And the satellite cones, some of them are isotropic, some are anisotropic, depending on whether they're at the corner of the Brillouin zone. Yeah. Yeah.
Satellite cones, are they at the endpoint or at the A point?
Well, actually, this picture is a square lattice. So I'm calling it gamma, X, and M. So M is pi pi, and these would be 0 pi pi 0. And yes, trim points. Yeah, so they occur at all the trim points. Time reversal is what protects them. If they're at gamma or M, then they're isotropic. If they're at corners, you only have two-fold symmetry, so they're anisotropic. Yeah, exactly. Right. And so we can see these things. We can also see them in the density of states as these dips here. So when two satellite cones are nearby in energy, the dip doesn't go all the way to 0. But if you have one which is isolated in energy, then you can see the density of states dipping to 0. So we can track these, they move around. And if you were to do the experiment, you would see these dips in the density of states appearing, and that would correspond to these satellite cones. And this is again related to the reason we can't get gapped mini bands, because the satellite cones can't gap because they're protected by time reversal. And again, that's the difference between this system and twisted bilayer graphene system. Okay, so that's our perturbative result. We computed the velocity, and we can also see these satellite cones, and we can track their energy and velocity. So then the next question is, do we think that how much can we trust the perturbation theory? It was a very, very simple model. So you might be worried, well, we use this isotropic Dirac cone and we only looked at the surface. It ignores any anisotropy, which we know occurs to higher orders. And then secondly, it ignores any coupling to the bulk bands. So those are the things that we want to address. And so that's why we made these 3D bulk models that I'm now going to describe. So there's two bulk models. Each one is on a different aspect. So I said there's two ways we can get a potential. One is a twisted heterostructure, which is putting some 2D material on top of a 3D TI, and the other is imposing a superlattice potential directly. And so the first thing you study is this idea where we put some material on top of the 3D TI, and the degrees of freedom couple from one layer to the TI surface layer. This will, if these two layers have almost the same lattice, then if you twist them, you'll get some wave vector difference the same way that you do in twisted bilayer graphene. So we get some effective Hamiltonian. And what we want to do is integrate out this 2D insulator. Like I said in the beginning, that's why we chose it to be insulating. Its only effect is to put a potential on the surface of the 3D TI. And so when we integrate it out, then we get this kind of effective potential. And the way that this effective potential works is it basically, it combines two different interlayer coupling terms. So this form doesn't matter. The reason that I'm saying this is just to say, if you couple two different layers and you integrate one layer out, you get a kind of weird form of the potential. And so we're going to study this weird form, and we know what it is. Yeah, that's what I want to say. And to answer this question, are Dirac points and Dirac fermions identical in the cones? Yes, we're just considering the Dirac cone on the surface. It's linearly dispersing in the continuum model. But in this model that we're going to study, which actually has a 3D bulk attached, then it's an emergent feature, which at low energy, the Dirac point is this point, and the excitations are the Dirac fermions. Okay, so this is the model that we study numerically, and this is the potential that we choose to study. And the reason that we choose this is the reason I just said. When you integrate out the degrees of freedom on the 2D layer, you end up with quadratic terms. And so you get these kind of, it's like a cosine potential, but the cosines also double up in this way. We could have studied a different potential, but that's the one that we wanted to study. So it simulated this twisted heterostructure. So we make a 3D model of a 3D TI, just the Bernoulli-Zhang model in 3D, and put this potential on the surface. And so I want to show the numerical results for this. So the main result is that we can look at the velocity of our Dirac cone as a function of the coupling between the 2D layer and the 3D TI. So there's some coupling strength, and what happens if we ramp that coupling strength up? The result that we see, so this is the velocity of our Dirac cone that we're plotting in units of itself. So it starts at 1, and the dots are the numerical results, and the solid line is our perturbation theory, which we've extended to much higher orders to match. And so what we see is that the velocity of the Dirac cone dips down to less than half of its original value. So that's the main result. You know, the question that I was asking in the beginning is, can we get an enhanced density of states on the surface of the 3D TI with the superlattice potential? And what we show is that, yeah, the velocity goes down by a factor of 2. And so the density of states is going to increase in the same way. And the perturbation theory and the numerics are actually, you know, relatively close over some range. If you remember, the perturbation theory keeps dipping down, and it looks like numerically this will come back up. There's some limit to how much we can actually flatten this. And we can also track the velocities of all of these satellite cones. And it looks like there's some kind of magic angle here. But again, it seems like the actual system is avoiding any types of magic angles. We never actually in numerics see the velocity of any satellite cone here crossing 0. And then we can also track the velocity as a function of wave vector. So small wave vector is kind of the analog of small twist angle. And so what we see is that as the wave vector is going down, again, these dots are our numerics, it's actually kind of seems to reach about the same point, around half of its original value, which is more or less the same minimum that we see when we vary the interlayer coupling strength. And so from this model, what we see is that, yeah, we can change the Dirac cone velocity a lot, and somehow numerically it seems to be limited to reaching about half of its original value, although I have no idea where that 1/2 is coming from. And then we can also look at the band structure, and we can see, like I said, all of these satellite cones correspond to these dips, and we can kind of track them. But one of the interesting features that we didn't predict is that actually there's at certain, so this is as a function of the interlayer coupling strength. And we get these different satellite cones. And as you change the coupling strength, these satellite cones move around in energy, and they don't all move the same. And so then sometimes they align with each other with some fine tuning. And so like this is an example of that. And this is actually where we see a really big peak in the density of states. So we're looking for a peak in the density of states or an enhancement that comes from an enhanced velocity of the Dirac cone. But actually the most notable peak that we see is when these satellite cones align with each other. And so, so this is kind of where we get the flattest bands. And this is something that we weren't expecting from the first place. It just comes out of the calculation. And so then the kind of the last thing that I want to say is, well, we wanted, so our toy model is that I just showed you is a square lattice of the BHZ model. How does this apply to actual materials? So we wanted to apply this to bismuth selenide. And so we took bismuth selenide, and what we were thinking was, what if we put hexagonal boron nitride on top? Because these things are actually pretty closely lattice matched. But it turns out that they're not lattice matched enough. And these wave vectors that come out are too big. So basically you want a wave vector that only couples surface states to surface states, but the wave vector is big enough that it's going to couple to the bulk states. And you know, this is what I've drawn the Q maximum. It's a really narrow window. And so we didn't really find any materials that would give us this, that would give us the right conditions. And so what we instead decided to do with bismuth selenide was the second approach I mentioned, just impose a superlattice potential on top by some patterned gate. So that's the thing that we're going to actually simulate here on this setup, where we have some gate, we have some patterning, and we create some cosine potential. It's going to be a 2D cosine potential with triangular lattice symmetry. And I just wanted to point out, you know, this is the reference that we were talking about this morning with some people. These types of pattern dielectrics have been realized in other systems. This is a paper by Corey Dean's group, and they realized a pattern superlattice on graphene. The lattice scale is like 35 nanometers, and the potential strength is about 50 MeV. So that's about the scale that we're thinking of. And yeah, it's been realized in the experiment, which is, you know, gives us some hope that it could also be realized in this system. And so what we did was make this ab initio model of bismuth selenide. So this is a bulk model. Well, it's five quintuple layers, so it's a slab model. And the gray is actually, the gray is the ab initio calculation. The red is our wanierized type binding model. So if we zoom in on the low energy physics, you can see the type binding model and the bulk model line up pretty well. So we're just going to have this wanierized, we're just going to use this wanierized type binding model. And then we're going to impose this triangular superlattice potential. And so I just want to show, this is kind of the main result here. First, we track the energy of the Dirac cones. This is just to see how things agree with our perturbation theory. But the important thing is that we track the velocity of these Dirac cones. So this red is the original Dirac cone, and the dots are our numerical data. And the thing that we see is that the Dirac cone velocity is dipping down again to, like, let's just say 0.4 of its original value. This is as a function of the potential strength. So, so it seems to reach like more or less the same max that we saw in our toy model, like dipping down below half of its value. But the neat thing is that this actually happens, and in this real system, which has a whole bulk and has all of the surface anisotropy that you would get from bismuth selenide. And we also study the band structure, and we can see again these different peaks and dips, and we can actually track them. They correspond to different satellite Dirac cones. The final thing to mention about this is one of the satellite cones itself actually has 0 velocity. And I don't know if that's actually related to the Van Hove singularities that you guys see, or if that's totally different physics. Actually, I think it might be different. That's occurring in the center of the Moire zone. And we understand why this is, and we can understand it perturbatively as well. So in summary, the parting message that I want to say is that we can look at other systems and try to see if we can get the same exciting correlated physics that we get in twisted bilayer graphene, but translate that to topological systems. And the hope is that we would get correlated topological phases, like topological superconductivity, one of the long sought after goals of this field, without realizing as complicated heterostructures. And so in the end of the day, through our perturbation theory and our models, we found 3 ways that we can enhance the surface density of states. One is we can renormalize the velocity of the original Dirac cone by a factor of 2 or slightly more. The other is this thing that I've drawn here. Different satellite peaks can align, which give you flat bands, which can give you a peak in the density of states. And then finally, there can be satellite cones with 0 velocity. So these are all interesting things that will lead to enhanced density of states. and possibly other correlated topological phases if we were to look at the interacting instabilities. And I think there's a lot of future directions to go with this. You know, one question is, can we find any material that we could put on the bismuth selenide surface that would give us near lattice matching? That would be really interesting. The other is looking at gapless 2D materials on the surface of the 3D TI. That's because they do more than just impose a potential, because then you actually have interlayer coupling. And then finally, of course, this big question is, well, what are these interacting instabilities? And of course, Liang's group has written some nice paper looking at a similar model where they find that the superconducting TCs can scale polynomially instead of linearly, instead of exponentially in the electron-phonon coupling. And that comes from these higher order Van Hove singularities. And so I think there's some interesting future question. Can we extend this model, which is a continuum model, to be more realistic simulation of bismuth selenide surface? And what are the interacting instabilities there? And how does that carry over? Okay, so that's everything that I wanted to say. Yeah, I'll be happy to take any questions.
Thank you so much. There is actually a question that popped up in the
Yes.
Q&A, not the chat.
How is Berry curvature distributed in the 3D Dirac cone of the 3D TI surface state? Would the bands appear on the higher energy when the superlattice is introduced to be topological as well? Yeah, so the Berry curvature in the Dirac cone of a 3D TI, Berry curvature is concentrated. Berry curvature is concentrated near the Dirac cone, and so this would be different than, yeah, it's highly concentrated there. It's not evenly spaced. It's not evenly spaced at all, which is different than some of the flat bands and twisted bilayer graphene, where the Berry curvature can be relatively small spacing compared to, or small modulation compared to the Berry curvature of a Dirac cone. Okay. Any other questions?
More about the satellite cones with zero velocity.
Oh yes, yeah. So right. So actually, this is what happens. Let's see if I can go back. It wants me to quit. Yes. So
Could you say what the question is?
yes, I will repeat the question. Thanks for the reminder. So the question is, can I say more about the satellite cones with zero velocity? Yeah. So right, these are actually the Dirac cones at gamma in the Moire zone. Okay, so I don't know. Higher energy. Yes, higher energy. And so what happens, this is a special feature of six-fold or higher symmetry. So how do you get these satellite cones? You basically have 6 points that will fold onto gamma. Okay, and each point will be kind of coupled to it and its trim point will form one satellite cone, or it and its time reverse partner will form a satellite cone, 2 more points. Okay, so then you can ask, what's the momentum difference between each K point and its time reverse partner? And the momentum difference, if it's equal to 1 mod 6, so you get a mod 6 because you can only define momentum mod 6 because of the six-fold rotation symmetry. So if it's equal to plus or minus 1 mod 6, then you'll get a velocity. But if it's not, there won't be a linear overlap between these. The linear term will vanish. So these, so you get 3 satellite cones. So you get 3 satellite cones, and 2 of them can have linear dispersion. And I suspect this thing has a quadratic dispersion. So flat may have been an optimistic thing to say. It has no velocity, but there's no linear velocity. There's no reason to think that the quadratic velocity doesn't vanish. Does vanish. Yeah, it probably is non-zero. Yeah. So I don't know. So in your paper, the interesting physics is happening at the K point of the Moire zone. Yeah, exactly. These are at gamma. And so what I don't know, we just track them at gamma because there's too much to track, but I don't know if you get the same thing happening at K. And I don't know if the disappearing to linear order is related to the higher order Van Hove singularity, which is also a higher dispersion. So these might be the same physics, but I haven't figured that out. Yeah. I see. Yeah, so that's, you're right, because it's at K. So it's probably different. Yeah, it's a generalization. Okay, good. Well, then that's a good time to end. So great. Thanks everyone for listening. Thanks for the questions.
Thank you so much.
Yeah. Yeah.